Hello everybody, my name is Danik, and today I will be sketching the function k of x equals 1/4 x to the fourth minus 9 over 2 x squared. This will be my first video of many covering the Ontario Advanced Functions and Calculus curriculum. Um, I think it's best that I start off with graphing polynomial functions, given that the first two units of advanced functions and calculus work up to this. So how are we going to graph this? Well, we're going to use some of our knowledge of end behavior, um, uh, points of inflection, concavity, uh, critical points, x-intercepts, and so on, so that we can graph this function to our best degree. All right, so let's start with step one. Okay, so step one. Are there we want to know if there are any restrictions on this function. And given that it is a polynomial function, there are no restrictions, no vertical or horizontal asymptotes. So we can write no restrictions. Our second step would be to find the x-intercepts. So how are we going to do that? Well, we set the equation equal to 0. So 0, well, we set the function equal to 0. 0 is equal to 1 over 4 times x to the fourth minus 9 over 2 times x squared. All right, so we could use long division or synthetic division, but I don't see any need for that, given that we know that there's a common factor in this equation. And what is a common factor? Well, x squared. Oh, actually, it's 1 over 4 x squared. 9 over 2 can be divided by 1 over 4. So 0, to give us a whole number, so 0 is equal to 1 over 4 x squared, and then x squared, right? Because x to the fourth divided by x squared, right? X to the fourth divided by x squared, that give us x squared, and the 1 over 4 divided by 1 over 4 is just 1, so we don't have to write the 1. Minus, so what is 9 over 2 divided by 1 over 4? Let's plug that into our calculators. So 1 over 4, and we get 18. So 1 over 4 x squared times x squared minus 18. All right, so what will make this equation equal to 0? Well, the factors are equal to 0, so let's set both factors equal to 0. So 1 over 4 x squared is equal to 0, and x squared minus 18 is equal to 0. So what is 1 over 4 x squared equal to 0? Well, it's just 0, right? The square root of 0, right? I mean, so first step would obviously be to divide both sides by 1 over 4. So 0 divided by 1 over 4 is just 0. And then square root of 0 is just 0. So uh, our first x-intercept, and I'm going to label that as x1, is equal to 0. So what is our second x-intercept? Well, x squared, and we move that negative 18 to the right to make it positive, is equal to positive 18. And now we take the square root of both sides, right? These cancel out. So x is equal to plus or minus, well, what is the square root of 18? Plus or minus 4.24, approximately. So our x2 is approximately equal to 4.24, and our x3 is approximately equal to negative 4.24. All right, so over here, I'm gonna label x int, so for x-intercepts, and where are x-intercepts? Well, 0, 0. Uh, let's do this in red. Okay, so 0, 0, 4.24, comma 0, and negative 4.24, comma 0. So Now, our next step would be to find our y-intercept. So, step 3, y-intercept. Well, we don't really have to show any work to solve this, right? Um, we know that this is written in standard form, and this would technically be plus 0, right? So that would be our y-intercept. And we also know that our x-intercept is at 0, 0. So, well, even if you want to know how it works, well, you just plug 0 into this. So 0 to the 4th is 0 times 1 over 4 is 0 minus 9 over 2 times 0 to the second is 0. So 0 minus 0 is 0. So our y-intercept is at, well, 0, 0, right? Our x and y-intercepts share a common point. So y int is at 0, comma 0. All right, step 4. You know what? Let's plot down these points right now so we don't have to do it any later. All right, so our first intercept is at 0, 0, right? Our next one is at 4.240. So if this is 4.5, I mean, if this is 5 and this is 4.5, then 4.24 would be approximately there, right? So there's 4.240 and negative 4.240. Well, it's the exact same thing, but the opposite side. So negative 4.240 would be approximately right there. All right, and in case you forgot, our y-intercept and our x-intercept share the same point, so we don't have to plot them twice, right? Now they would be overlapping each other. All right, so step 4. What is step 4? Well, let's find our critical points. And what are our critical points? Well, our critical points determine whether our function is going from increasing to decreasing. So, like this, decreasing to increasing, like this, increasing to increasing, so something like this, or decreasing to decreasing, so something like, sorry, something like that, right? And obviously, these are just rough sketches, they're not accurate, but what do we notice about these mini sketches that I just drew? Well, they all have a tangent of 0, right? Horizontal tangent gives a slope of 0. And therefore, how do we calculate the slope of this tangent at that one point? Well, we use our first derivative. So we can set our first derivative equal to 0 to find our critical points, which could be possible maxes or mins, or neither, right? This is neither a max or a min, but it's still a critical point as it's where the function has a slope, a horizontal slope, and it would be really crucial to graphing function our sketch, right? So let's erase this real quick. And step 4, well, before we can set it, our first derivative equal to 0, we have to find our first derivative. So k prime of x, so k prime of x, right? That's the first derivative of x, is equal to, so x to the 4th, we multiply the 4 here, and that just becomes 1, and we subtract 1, and that becomes 3. So equals, and we don't have to write 1x, so just x to the 3rd minus, bring the 2 over here, cancels out, and we're left with a 9, and we subtract 1, so we have x to the 1, we don't have to write x to the 1, so minus 9x. And again, like we did in the in the second step, we can common factor. What can we common factor? We can common factor an x. So k prime of x, our first derivative of x, is equal to x times x squared minus 9. And now we set it equal to 0. And what would make the equation equal to 0? Well, the factors are equal to 0. So we set this one equal to 0. So x is equal to 0, and there's nothing else we can do, so just x1 is equal to 0. And we set this one equal to 0, so this would be x squared equals 9, right? We move the 9 to the right, negative 9 to the right. And what is the square root of 9? Well, just 3. So our second x value of our critical point is 3, and our third x value of our critical point is negative 3. So now we can write down our critical points. And where are our critical points? Well, we plug these values back into our original function. So k, so k of, sorry, so k of 0 equals k of 3 equals k of negative 3 equals. So if you plug those values into your calculator, k of 0, well, we know what k of 0 is, right? From here or here. So k of 0 is equal to 0. And what is k of 3? All we got to do is plug 3 into here and here. And if you put that into your calculator, you should get a value of approximately negative 20.25. And just a quick note or tip, if you took advanced functions, and if you're taking calculus, you should be taking advanced functions, you would know that this is an even function. And what do we know about even functions? Well, we know that it is symmetrical across the y-axis, right? So like this is an even function. This would be an even function, right? Because it's symmetrical along the y-axis. So what does that mean? That means our opposite points should give us the same y value. And if we look at if we look at, for example, these x-intercepts, so 4.24 and negative 4.24, we have zeros. There are x-intercepts, right? And they are opposites of each other. So because it is an even function, I can assume that this is negative 20.25. And in case you don't believe me, just plug it back into your calculator and you should get negative 20.25. It's pretty straightforward. And if you don't get negative 20.25, then you're probably doing something wrong. All right, step 5. You know what? Let's graph our critical points so we don't forget it. Okay, so 0, 0, we already have that. Wow, 0, 0 has a x-intercept, a y-intercept, and a critical point. It's pretty important. 3, negative 20.25. So we go to 3, so 3 would be around there. And negative 20 is here, negative 21 is here, negative 20.5 is there, and negative 20.25 is right around there. Oh man. And negative 3, right? And negative 20.25. So just copy what we did on the other side. So right around there. All right. So we have our critical points and our x-intercepts out of the way. What is next? Well, our second last step would be our points of inflection. That is where our function will switch from concave down to concave up, or concave up to concave down, right? What does that look like? Well, concave up to concave down, or concave down to concave up, right? It's where the function switches in concavity. Okay, so and another quick note I have to mention, we could use the second derivative test to make sure that these are maxes or mins, right? Because these are still possible maxes or mins. We don't know for sure. But I'm not going to do that, and I'll show you why near the end of the video. So, step 5. So how do we find these points of inflection? Well, we set the second derivative equal to 0. And before we can do that, once again, we have to find our second derivative. So k double prime of x equals 3x squared, right? Move the 3 down and then minus 1. So 3x squared minus 9. And now we can set it equal to 0. So 0 is equal to 3x squared minus 9. 9, we move that 9 to the right, is equal to 3x squared. Divide both sides by 3, so divide by 3, divide by 3, and 3 is equal to x squared. And I'll square root both sides, and we should get a plus or minus answer. So x1 is approximately equal to, and x2 is approximately equal to. Okay, so let's plug root 3 into our calculators. Root 3. And you should get a value of approximately 1.73. So 1.73 plus or minus, right? So negative 1.73. And these are our possible points of inflection. They are not guaranteed to be points of inflection, but already from what I know about this function, I'm pretty certain that they are. But for the sake of it, we're going to do our charts, our table of values. No, our chart. And with this chart, we'll be able to test whether or not our critical points are maxes or mins, and if our points of inflection are points of inflection. And on top of that, we'll be able to see we'll be able to properly visualize how the graph changes over its domain. So this is why I did not want to do a second derivative test, even though you could, but I feel like it's easier doing it this way. Okay, so step 5, and I'm gonna need a little bit of space, so I'm gonna make this a little bit smaller. So step 5, step 6, sorry, and this is our second to last step. Our last step is obviously graphing or sketching. Um, so how do we make this chart? We first have to include our negative infinity, our positive infinity, and then in between we put our critical points and possible points of inflection. All right, so now let's pick some test values in between. So let's choose some easy points. So -4, -2, -1, 1, 2, and 4. All right, so right here, we're going to write f, let's write our first derivative, so f prime of x. And over here will be our second derivative. So, sorry, not f. We're not using f in this case. We're using k. It's still a function, but we're running as terms of k of x. So our first derivative of k of x, and then at k double prime of x, and then our original function. So k of x, and you're going to see how useful this is when it comes to graphing. I mean, you don't have to do this, but I feel like it is better. It is a lot easier to graph when you do this. Okay, so from negative infinity to -3, let's plot that point of -4 into our first derivative. So here's our first derivative. And if we plot that point in, we should get, let me just put that in real quick. So 3 times -4 to the power of 3. Remember to put it in brackets. Minus 9 times -4. And I get -156. Remember, we don't care about the value. We only care about the sign. So let's write a negative. And now let's do the second derivative. So our second derivative is over here. So 3 times negative 4 to the power 2 minus 9. And we get 39. Again, we don't care about the value, we only care about the sign. And I'm going to let you guys do the rest of this table. I don't really feel like plugging all these values into my calculator, so um, I'm going to solve these really quick. So positive, 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 negative, 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 uh, negative, positive, and positive, positive. Okay, so now that we have all of that, we can write how our first derivative and our second derivative are affecting our original function. So between negative infinity and negative 3, so when x is less than negative 3. So when x is less than negative 3, the function is decreasing. So I'm just going to write DEC is decreasing. Remember, when the first derivative is negative, the original function is decreasing, right? So from negative infinity to negative 3, and the second derivative, it is positive. Therefore, the original function is concave up. Remember, the second derivative tells us the concavity of our original function. So it is concave, all right, C-O-N-C period, up. Okay, so what does that look like? So if we're decreasing, we're obviously going down, right? And what does concave up look like? Well, concave up like that, right? So this is decreasing and concave up, right? We're decreasing and we're also concave up. So how about between negative 3 and negative 1.73? Well, we are increasing and concave up. So what does that look like? Well, you are increasing and you're up, concave up. So what does that tell us about k of x at negative 3? Well, it is it is a local min, right? This would look like that, and that would be a local min. So we already know that one of our critical points is a local min, right? So here, negative 3, negative 20.25, that is a local min. And now let's test our next interval. So between negative 1.73 and 0. So we are increasing and concave down. So what does that look like? Well, if you're increasing and you're concave down, you look something like that. Sorry, not like that. You look something like that, right? You're concave down and, sorry, it's a little hard to draw on this. Something like that. Okay, right? You are concave down and you are increasing. So what do we notice about this interval? Well, what did I tell you about concavity? A switch in concavity, right? From concave up to concave down. That would tell us that we have a point of inflection. And negative 1.73, right? So negative 1.73 was one of our possible points of inflection. Well, it's no longer a possible point of inflection, right? It's a point of inflection. So there we have a point of inflection. So now let's move on to the next interval. And as I said before, we know that this is an even function. So we don't have to finish, we don't have to really like look at these terms to know what the rest of these boxes are going to look like. We can just mirror both sides. So let's just do that real quick, right? We want to make our life easier when doing this, not harder. So that, and that, and that. So this side is the mirror of this side. Okay, so now we can start graphing. And before we start graphing, let me just uh, put our what we know. So this is a local min. So local min. This is point of inflection. So POI, no longer possible. It is a point of inflection. This is a local max. This is another point of inflection. And this is a local min. Alright, so now finally start the sketching process. Probably the reason you're watching this video. Okay, so from negative infinity to negative 3. So from here all the way to here, we are decreasing in concave up. So we should look something like that. Okay, that's not really the best representation, but you guys get the idea. Um, you know what? Let me just make this a little neater. You got time. Okay, so thing like yeah, it's still messy. Never mind. Okay, um, just know that it's trying to be it's trying to look like that. Okay, so we are decreasing in concave up, right? Decreasing concave up. From negative 3 to 1.73, right? This interval, we are increasing in concave up. So negative 3. Oh, and I forgot to plot our possible points of inflection. So let's just label them real quick. So K, sorry, let's write this in white. So K of 1.73 and K of negative 1.73. And if you plug those into your calculator, you should get approximately negative 11.23. And because it is an even degree function, then we know that this is also negative 11.23. Okay, so negative 1.73. So if this is negative 1, this is negative 1.5, 1.73 would be around there, and negative 11.2. So let's continue where we were at. So from negative 3 to negative 1.73, right? So from negative 3, from this entire interval, we are increasing in concave up. And you guys may notice that I'm being going really slow with this. If you guys want, you guys can just skip to the end of the video to get the proper graph, but I like to explain it in detail so you guys can properly understand what is going on. But that's just me. All right, so from negative 1.73 to 0, we are increasing in concave down, right? Our point of inflection. We were concave up and now we're concave down. Okay, so now we are increasing and concave down. Okay, that's a little too steep. Yeah, something like that. Okay, so now from 0 to 1.73, we are decreasing in concave down. I didn't write it, but we can already tell from here. So we are decreasing concave down. And then from 1.73 to 3, we are decreasing in concave up, right? That is our point of inflection. So something like that. Um, and from 3 to infinity, so when x is greater than 3, we are increasing. So after 3, we are increasing towards infinity. And I forgot to put an arrow there. So I'm gonna try my best to sketch this as accurate as possible. Yeah, I already failed, but you guys get the idea. Okay, this should be looking like that. It's just a little hard to sketch on this device, but it is what it is. Okay, so yeah, that is our final sketch. I tried to be as accurate as possible. Um, Here you have your point of inflection, and here are your local mins and local maxes. And as we can see, there is symmetry across the y-axis. Well, not with my garbage graph, but if you draw this properly, it would be perfectly symmetrical. And yeah, that just proves it is an even function, and that's our final result. Thanks for watching.